Page 40 is really the first explanation of probability here. And the first type of probability that they talk about is experimental probability. Experimental probability is when you actually do something and you count what's going on. So for example, experimental probability by flipping a coin means that you literally flip the coin 20 times and you count how many heads versus how many tails or whatever, whatever you're trying to get. If you're trying to get heads, how many heads compared to how many times you flipped it. If you're trying to get tails, how many tails compared to how many times you flipped it. Experimental probability will not always be the same as theoretical probability, which is what we're going to talk about next. Experimental probability, you have to make sure you do the experiment enough times. So like for flipping a coin, you're going to have to do it more than like 10 times probably. You may get 5 when you do it 10 times. But the law of large numbers tells us we probably have to do it about 100 times or more to get a true 50-50, which is what it ends up being. And so experimental probability is not typically used for something when you actually know the chances. Like with a coin, I know my chances. I have 2 sides. One of them is a head, okay? It's typically used for things that has a variable in it. The example they give us here is a baseball player. I mean, we can say all day long what their batting average is, but that doesn't necessarily mean that's what it's going to be because they're human, right? And so what we do is we take their actual number at bats and we get their actual hits or whatever, and we compare those two, and that is what we tell is their average, okay? And so that's an experimental probability. It's where they're actually doing the process and you're tallying up how many times they got the event that you wanted them to get versus how many times they did it all together. And so that's how you actually calculate it. If you look here at what they gave us as far as the probability definition, the probability of the event, you'll see it's a capital P and in parentheses is what they're looking for. And then how you calculate it is the number of times that event occurred over the number of trials or the number of times they tried it, okay? So the first example says, a baseball player got a hit 21 times in 60 at-bats. Find the experimental probability of his getting a hit. Based on the history of what he has done, what is the probability he will get a hit? All right? And so what we're looking for then is the probability of getting a hit. That's what we're looking for. And so we're going to put the number of times the event occurred, that's 21, over the number of times that he actually tried it. That is 60, all right? Typically, probability is done in percentages, not always, but typically. Sometimes they'll say 21 out of 60, but for at-bat, you're definitely going to hear a percentage there. And so you do want to convert it to percentage. So to do this, you are going to take that 21 and you're going to divide it by the 60. And then you are going to multiply that by 100, or you're going to move that decimal place over 2 places. And so you're going to say there's a 35% chance that he will get a hit if he is at bat. There's a 35% chance, all right? And so that's your probability. The event, total number of times it happens, over the total number of times that you tried it. So do check understanding number 1 there. And they do want it in percentage. So let's put it in percentage. We have 32 free throws out of 50 tries for this one. What is the experimental probability of her making a free throw? So you should have put 32 over 50 here. When you divide it, you would have gotten 0.64, and your percentage then would have been 64%. All right, let's look at the concept of theoretical probability. The first thing they talk about right above this is the term sample space. When you roll a number cube, the possible outcomes are 1, 2, 3, 4, 5, and 6. The set of all possible outcomes is called the sample space. So for theoretical probability, you have a set space that can happen. So if you have a number cube, there's only 6 possibilities. It's not like when the guy was throwing the free throws and you were just kind of counting. You know exactly what it is, and that is your sample space. And so with theoretical probability, you don't have to actually do the process. You can base it off of the known factors of what you have, all right? It's called theoretical because it's, in theory, that's what should happen, just like with the coin. In theory, with a coin, you should get it 50% of the time. What actually happens is different depending on how many times you do it, all right? And so it's important that the sample space be counted because it is a theoretical probability. With experimental probability, it's important that you have enough to actually give an accurate example. If we had done the basketball and they had only thrown 4 times and they made it every time, 100% chance of them making the free throw every single time is probably not accurate because they haven't done it enough to see if that's what they actually do. But with theoretical, it's known. We know how many numbers are on a number cube. We know how many sides are on it. And so we know that that sample space is specific. So with theoretical probability, it says if a sample space has n equally likely outcomes and an event A occurs in m of these outcomes, then the theoretical probability is m over n. Lots of words. What they're saying is you have a number cube. It's not weighted, meaning it's a fair cube, right? Then each side has an equal opportunity to be face up when you roll it, right? Unless something's wrong with it, it has an equal opportunity. If you're looking for a specific number, let's say number 2, that happens 1 time out of 6. So your probability is going to be 1 out of 6, all right? If you're looking for even numbers, that's going to happen 3 out of 6. Your probability is going to be 50% there. So all it's saying is what you're looking for out of the total sample space. This is how you're going to calculate this particular one. All right. So example 3 actually just said, find the theoretical probability of getting an even number when you roll a number cube. Well, there's 3 even numbers on a number cube, 2, 4, and 6. And so I have how many times what I want occurs, the probability of an even number here. 3 even numbers happen. The total sample space here is 6. That's going to be 50%, or 1 out of 2, 1/2. All right. So theoretical is a known amount of information. So let's look at check understanding number 3, probability of getting a prime number. All right, for this one, what should you have gotten? Hopefully 50%. Questions on that? Yeah, anything greater than 1 that is only divisible by itself and 1. So on the number cube, that would be 2, 3, and 5. Again, it would be 3 out of 6 or 50%. All right. So one of the things you see in biology is genetics. Genetics is very much probability based. The example they said is fold your hands so the fingers interlaced. Do you naturally place your left or your right thumb on top? So if you do this, which finger goes on top, right? And I would venture to say if we counted, let's see, we'll count. So how many of you, it is your right hand on top? That would be 1, 2, 3, 4, 5, 6. All right, how many is your left hand on top? 1, 2, 3, 4, 5, 6, 7. All right. So we're at about, close to 50-50, right? I don't think I counted one of y'all. All right. So this says when a parent has both a dominant and recessive gene, then 2 genes are equally likely to be passed to the child. If you have 1 or 2 dominant genes, you normally place your left on top. Suppose a child has parents who have just 1 dominant gene. What is the theoretical probability they will naturally place the left thumb on top? And so what you see is, so this is actually just a way to show the probability. They have the gene from the mother, capital letter being the dominant, lowercase being the recessive, father, capital being the dominant, lowercase being the recessive. And then you just fill in the blanks here, which is kind of easy to do. But the dominant gene will show up. And so if you look at how many times it shows up and the chances of it showing up, then you can see that it's going to show up 3 out of 4 times, right? And so the probability of this particular child having that trait is about 75%. Now, this is a probability, right? So I have blue eyes, my mom has green eyes, and my dad has brown eyes. Blue is recessive. This probably tells me that they each had a recessive blue eye gene for them to have me, right? I had a 25% chance of having that. Out of their 2 children, only one of them had blue eyes, right? So the other one did not. And so you can see that while your probability might be high or low, it doesn't necessarily always happen because it is a probability, right? It means that every time you can have a blue-eyed child or every time you can have a recessive gene show up. It just, this is the statistical chances of it. This is theoretical probability. Yeah, so the probability of it being recessive then would be 25%. And that's what you're going to find with probability. If you have one probability and you want the opposite, they should add up to 100%, right? Because, I mean, those are the only options, okay? And so if you have the probability of some event and then the probability of that event not happening, those two should always be 100%, because it either happening or not happening are your only options, all right? And so they'll add up to 100% just like this one did. All right, geometric probability. I think we touched on this a little bit in geometry, geometric probability. This basically takes a geometric figure, and then you have your probability of something happening within the figure itself, all right? Either they do it with like shading, or they do it with like, this is a prime example, a dartboard. It says, suppose that all the points on the circular dartboard shown at the right are equally likely to be hit by a dart you have thrown. Find the probability of scoring at least 10 points. At least 10 points, all right? And so when they want you to score at least 10 points, you are going to calculate what the probability is of 10 points or more, okay? 10 points or more. Now, the important part here is that you don't just count the rings. Like, I have 4 rings. One is 10 and one is 20. I'm not going to say, oh, well, 2 out of 4 rings, it's 50%. That's not how this works with geometric probability. I actually have to calculate the radius here and the area that I'm trying to hit, okay? And so they tell me here that these little guys are 2 inches. So each ring here is 2 inches, and that's really important. So if I know this is 2 inches, that means this is going to be 2 inches, this is 2 inches, and this is 2 inches, okay? It's kind of hard to see, so I'll do it again. So each of those are going to be 2 inches. All right, and so then I have to look at the probability of hitting the inner circles that I'm trying to hit compared to the probability of hitting the whole board. And we're going to assume you actually hit the dartboard, that you don't go outside of it, all right? And so for this one, I have to actually take what I want. Well, I want at least 10 points. Well, that means I want 10 or 20 points. I want to be in this circle right here. What is the radius of that circle if they're each 2? Yeah, it's 4. So then what's the area of that circle? So what's my formula for area of a circle? Pi r squared, right? And I'm going to put that over the entire circle. Well, what's the radius then of my entire circle? Yeah, it's going to be 8, right? Everybody agree with that? So I want to say, well, if I want 2, 4, 6, 8, so pi times 8 squared, right? Everybody agree with that? That would be my probability. Now, what do you notice about the pi's? What can we do there? Yeah, we can cancel them out. So it ends up just being 4 squared over 8 squared, right? Which gives us what? 16 over 64, which is what? 1/4, which is 25%. So even though I can hit 2 out of the 4 rings, it's not 50% because those are smaller circles. It's actually a 25% chance of me hitting those 2. So you're actually taking the area over the area. You're comparing the area of what I want over the area of what I have. So go ahead and do check understanding number 5 there. All right, let's look at these. Scoring 20 points. You just had to take the inner circle, which was a radius of 2, over the entire circle, which was a radius of 8. And you should have gotten 1/16, which is 6.25%. 6.25%, right? For the second one, you actually had to take a radius of 6 and subtract out a radius of 4 because you just wanted this 5. You did not want anything else. So you had to take the whole thing, subtract out this inner circle, and put that over the entire thing. And so for this one, you should have gotten 31.25% there. All right, 31.25. Let's look at the second one really quickly. So I am going to take this circle here, this 5, and I'm going to subtract out the 10 because I only want, oh, we don't want that. I only want this ring, the 5 ring. And so to do that, I have to take the pi, and it's 1, 2, 3, so 2, 4, 6, pi 6 squared, pi r squared, and I'm going to subtract out these 2, so pi 4 squared over the whole thing. All right, my pi's will still cancel, so I end up with 36 minus 16 over 64. All right. Which is going to give me my 5 over 16.